All right, so as mentioned, today we're going to be talking about how the recently very successful AlphaGo system works. So let's start with some words of introduction. AlphaGo is, as you already know, a Go playing agent that was developed by DeepMind. First, they have managed to defeat the European Go champion, Fan Hui, with a score of 5-0. And some months later, they perfected the system a bit more and managed to beat one of the greatest players of all time, Lee Sedol, with a score of 4-1. And as many people have already said, this is one of the greatest AI achievements to date, simply because many highly ranked AI researchers were predicting that we were not going to be able to achieve something like this in the following 10 years, at least. This talk will primarily be a digest version, so a relatively high-level overview of the original publication that DeepMind made, so Silver et al. In Nature in 2016, Mastering the Game of Go with Deep Neural Nets and Tree Search. So this is what it looked like. Here you have the AlphaGo system, which has a view of the board, and it gives moves for the human coordinator to play. And on the other side, you have Lee Sedol being very nervous, because he himself admitted he did not expect an artificial intelligence system to play at such a level at this point. When I first saw this result, I was very excited, and I spoke to several of my relatives about this, like, this is very huge. We managed to do this. It's incredible. And an actual response I got was literally written down here. So why are AI people always so proud of solving games? Why don't you solve something useful for a change? And that's indeed a good question. And I think I have a good answer. Essentially, the reason why games are so good for artificial intelligence research is because they have clearly defined rules, and it's clear to infer what the current state of the game is. The real world, as we will see in the next slide, is often far worse and sometimes quite subjective. And the major implication of this result, as we will see, is that if you have a game, an environment that has exponentially complex state space and transitions, such as Go, we can actually achieve superhuman levels of performance without exploring any significant portion of the search space. In fact, AlphaGo, in the winning matches against the European champion, has explored less states per turn than Deep Blue did when it defeated Garry Kasparov in 1997 in chess. So it is actually quite a significant result. And this is just an example of how real-life machine learning problems can be unfair. I hope that some of you have already heard of popular datasets such as MNIST and ImageNet. And these are some examples of images in the testing datasets for these tasks where it's not really clear, even to a human, what the correct result should be. So in MNIST, your task is to infer what digit was written down. And I hope that you can see that for some of these examples, this is pulled from the actual data set, that there are some examples where it really isn't clear what the numbers should be. And actually, in most of these tasks, human performance is not at 100%. An even better example is the ImageNet classification task, where you have a bunch of colored images, and your AI has to figure out what is the object that's the focus of the image. And I believe that none of you will tell me that the focus of this image is a popsicle, or that the focus of this image is a plunger. And there are some other really interesting examples, like you have a whole stationary set in here, yet the class of this image is a ruler. So this is just an example of how the real world does not always treat us nicely, and why it's actually a good idea to test bed our algorithms on games. So this is now a very outdated XKCD where the complexity of several games has been enumerated in order of increasing difficulty for computers. So you have games such as Tic-Tac-Toe and Nim, which are completely solved for all possible positions. You have Gomoku and Checkers, which have been solved for all starting positions, so a computer can play optimally. And you have the second part of this image, which is largely outdated by now. So computers can beat top humans: Scrabble, Counter-Strike, beer pong, Reversi, chess. Actually, the last time a human managed to beat a top computer in chess was 2005. And this region, at the time, were all games where computers still lost to grandmaster level humans, but focused research and development could change this. And in fact, you've probably heard of IBM's Watson, which became a very successful Jeopardy player. Texas Hold'em poker was solved for some specific starting conditions. Arimad was solved last year. It's also something that I'm going to mention briefly in the introduction, and Go. The final part of this image is computers may never outplay humans, and you have games such as Snakes and Ladders, which is completely a game of chance. And this game, Mao, is essentially a card game where everyone knows the rules, but when someone new joins the card game, he has to infer the rules from how other people are playing. So you're not told the rules when you start the game. And some people are saying that if we were ever able to make an artificial intelligence agent to crack Mao, that would actually be a very good step forward towards general artificial intelligence. Because you need to be able to figure out what the rules are just from observing what the other players are doing. And in all of these previous games, the rules are very clearly defined. So I'm going to get towards the algorithm that is at the core of AlphaGo by starting off with some easier examples, starting from something that's easily solvable deterministically across some algorithms that require a bit more heuristic approaches all the way up to Go. So the first thing that I'm going to talk about is tic-tac-toe. What's really nice about it is that there is a very small number of potential states a board can be in. It cannot be more than 9 factorial, which is relatively small for today's computers. And that means we can create a directed acyclic graph where nodes are the states of our board and edges represent moves that people take. And you have terminal states where someone has either won or the game is drawn. And this is what this graph might look like. So you start from an empty board and you have up to rotation and variance 3 possible places where X can play the first move, and then O can play on these independent positions in the next move. You can easily build this tree up. There's not that many nodes, and it's fairly easy to write a program to do this. Because the state space is so small, we can go down to all the terminal states, figure out whether it ended in a win for X, a loss for X, or a draw, and then backtrack from there to determine which states are winning for X, losing for X, or ending in a draw, assuming optimal play, of course. And that, of course, means that the starting state, assuming that both players play optimally, is always going to be a draw state. Actually, this is another XKCD where this was very nicely enumerated. So if you generate this entire tree and figure out what the optimal move for X and O should be at each possible step, depending on the board state, you end up with a nice visualization like this. So if you're X, your optimal first move is always playing in the corner. And then depending on what O does, it's one of these options. You're going to play next somewhere here. And sometimes, if O is not clever enough, you're going to be able to snatch a win. But usually, it's going to end in a draw. Moving on to chess. Chess is a very, very old game. And people have been researching it for as far as AI was a thing. So the first research on chess began in the 1940s. First agents were devised by the end of the 1950s. And high-ranked players were already defeated in the 70s. And this great event in 1996 is when Deep Blue played the first game against Garry Kasparov. Deep Blue managed to win 2 games, but eventually lost the series. However, already in 1997, Deep Blue managed to defeat Garry Kasparov 3.5 to 2.5. And this was, at the time, an event of a similar magnitude the way AlphaGo is now. Deep Blue was developed for 7 years by IBM, and at the time it was a state-of-the-art parallel supercomputer which had 256 CPUs at 120 megahertz each, which allowed one to do about 10 giga floating point operations per second, which is very small compared to today's supercomputers, but for the time it was quite sophisticated. And the key ingredient of how IBM was able to crack chess was something called an evaluation function. It's a mathematical structure that takes in a state of a chessboard and gives you a number. This number tells you how valuable this current state is for white. So obviously white wants the number to be as high as possible, black wants the number to be as low as possible. Sometimes in AI literature, we refer to the guy who wants to maximize the score as max and the guy who wants to minimize the score as min. And the algorithm that solves this kind of problem then is called minimax. There are several important ingredients that take part in this handcrafted evaluation function. So you actually look at the material advantage, so which player has more pieces, which player has better position, which player has protected their king better, which player has had more tempo in the past few moves. So it's actually a handcrafted function that takes in a state and always deterministically will give you the same answer. And this is a very difficult problem. And being good at making a function for one problem will not make you immediately good at making a function for another problem. And now, how can we use this evaluation function? Well, the key idea is we would ideally want to use the same algorithm that was used for tic-tac-toe, like generate the entire graph of all possible chessboard states and moves and figure out from the terminal states which are the optimal place. However, chess has a relatively large branching factor and a lot of possible states the board can be in, and therefore we really cannot do this. So we do a heuristic approach. We don't go all the way. We just consider k moves in advance. And we stop searching at that point. And this is where the evaluation function comes into play. Because when we stop searching, we have not necessarily reached a terminal state, a checkmate state, or a stalemate, or something like that. So we have to use this evaluation function to give us the value of these states. And then once we have these values, we can just reuse them in the same way as we would a ±1 or outcome for tic-tac-toe. However, we're still not quite there yet, because a modern computer would still need about 2 minutes to generate 3 to 4 moves deep, when a typical grandmaster player in chess is able to think 10 to 15 moves ahead. So this is still not good enough. We need to find a way to be able to go deeper while still not sacrificing accuracy. And it turns out that there is a very straightforward way to make that work. Essentially, as we go through this minimax algorithm, the first player, max, will always choose the branch which has the largest value, and the min will always choose the branch which has the smallest value. And if at some point we have a candidate solution which is definitely better than whatever the current branch could possibly give us, we can completely cut off that branch and not consider it at all. And this algorithm is called alpha-beta pruning. So imagine that we're playing this imaginary game where max is blue and min is red, and we have evaluated up to 2 moves deep, and we have applied the evaluation function for all of these possible states. And the game is relatively nice. It has a branching factor of 3, so at each position you can only play 3 potential moves. And I have already evaluated some values. So min will always choose the branch which gives the smallest value for max. And in this case, 6, 2, 3, the smallest one is 2, and therefore the value of this state for max is 2. Because if you go this way, the value is going to be 2. Now let's see what happens if we move here. Well, first of all, we write a tentative value of 2 here, letting us know that so far the best value max can have here is a 2. And now we explore this branch. What can we see? The first number we encounter here is a 1, which means that min can definitely achieve at least a 1. And that therefore means that if max plays here, he is going to get a 1 or worse, which is worse than the 2 that we already have. So the moment you encounter this 1 here, you can cut off this entire branch from consideration. So there is a 1 here, and it eliminates this entire branch because there's no way max will want to play here. So this is essentially what alpha-beta pruning is. It's a very simple optimization to this exhaustive minimax search. What actually happens is this is already sufficient to achieve grandmaster level play. So this allows you to go 10 to 15 levels deep, and it was sufficient for beating Garry Kasparov. I will briefly mention the game of Arimad, which was in the XKCD I talked about before. And grandmaster level AI for this game was only developed last year. In all the previous years at the Arimad Challenge, the human experts were always miles ahead of the computer systems. And the winning program, named Sharp, was designed by a researcher called David Wu. The game is designed to be very similar to chess in appearance. So it uses the same distribution of figures, and it's played on an 8x8 board, so you can play a game of Arimad using chess pieces. But the game is far slower in tempo. Each move actually involves you moving a figure for 4 positions. So there is a lot of movement at each turn, and it's very slow. In order to be able to capture a piece, you have to move them to very special regions of the board, and you have to plan your moves like several steps in advance. So it's designed to be very visual, and therefore very easy for humans to formulate a strategy. But computers have to think very, very far in the future, potentially, to be able to think of a perfect strategy. So just looking 10 to 15 moves in advance with the basic alpha-beta pruning is probably not going to be enough for a game of Arimad. However, Sharp was able to crack this game using exactly the same methods as chess. So they used alpha-beta pruning. However, there were some very clever state evaluation functions and some very clever heuristics as to which branches to explore first, to make sure that alpha-beta pruning has the most potential for cutting off as many branches as possible. So with these simple ideas, you're able to crack some very complex games, and this is what an Arimad board looks like. So it's not immediately obvious, but there is exactly the same distribution of pieces as for chess, and these 4 slots are capture slots. So you actually have to pull an opponent's piece into this slot and surround it by your figures in order to capture it. So that requires sometimes really careful planning and does not just require you to move in a particular direction and capture someone. So now that we went through all the essential tree search games that can be solved using this basic idea of minimax search and alpha-beta pruning, I will talk specifically about Go. It's played on a 19 by 19 board, so it's much larger state space than chess. The board is initially empty, and black and white take turns placing stones on a board. You may skip a turn at any moment, but then you have to sacrifice one of your stones. And after 2 consecutive turns are skipped, the game ends. There are some other interesting rules. The goal of the game is to surround more territory with your pieces than your opponent. And you can capture opponent's pieces. If you completely surround a group of someone else's stones, then this player's group is removed from the board as well. And there is a particular rule that is designed especially to prevent cycling. If you have cycling occurring in chess, that can usually end in a stalemate after several repeated moves. But in Go, you're actually not allowed to repeat a state of the board twice. That's called a Superhuman rule. So let's think back a bit as to what are the most difficult aspects of trying to write an AI agent that solves Go. The board is significantly larger than a chessboard, and a branching factor is much larger. Therefore, there are exponentially more possible states that you have to consider. State representation might be problematic. You need to satisfy this rule where your state cannot appear more than once, and there could be a lot of states you have encountered throughout a history of a particular game. And similar as for Arimad, the game is more a visual game rather than something that you can form easy rule-based strategies for, and therefore it's predisposed for humans to achieve really good results and not that good for computers. However, despite all of the above, as you all know, AlphaGo managed to do the seemingly impossible. So, how? The key problem of algorithms such as alpha-beta pruning is that in the worst possible scenario, they still have to consider a lot of branches. Because if you are not able to find a cutoff move, you are going to explore every single possible branch. And the branching factor for Go is just too large. You cannot do this and achieve a reasonable depth of play. One needs to consider significantly fewer moves than you can actually play in Go. And this problem was circumvented through this technique of Monte Carlo tree search. It takes in some knowledge that you have of the problem thus far, and based on it, it's going to discard a lot of the moves. Simply, you have some belief that, say, move X is much better than move Y. I'm not going to consider move Y at all in my search. And using this, you're able to reach far greater depths because at each step, you're only going to consider a very, very small fraction of the moves. And this graphic illustrates it, I think, quite well. So this is a potential layout of a Go tree. So you start off from a starting state, and there are so many possible moves that you can play. But Monte Carlo tree search is able to somehow determine that this move is very good, much better than the others, or at least in the top 5 or something. So it will focus on this branch in particular, and then on the next level, it will focus on this branch and so on. So a lot of the moves that you might be able to take and Go are simply discarded. They're not considered when you're doing this learning phase of the algorithm. And this is significant because it then allows you to go deep enough to be able to outrank a human player who is able to think for several moves in advance. Normally, like if you're going to do Monte Carlo tree search without any prior knowledge about the game, then you're initially saying all of my move probabilities are exactly the same. And then you will just choose a move at random, see how well it goes, and then update your beliefs, and then choose another move at random, and so on, completely uniformly. But that's not good enough for Go, unfortunately, because as you can see, the branching factor is just too large. And if you were to train it by picking random moves all the time and then updating your beliefs, it would take a few decades at least to train this entire thing and be able to get reasonable. So you need to be able to have good prior beliefs as to which moves better than others. And we will call this a policy function. So what is a policy function? It takes in a state of the Go board, and it tells you for all the possible moves a probability distribution. So how likely it is that a good player would play a move here. And then you can only initially focus on those that get really high probability values. And this then gives you a very good initial belief if you're able to design a good policy function. And then as you go along, you might find a path that was slightly less likely, but it ends up giving you greater reward. And then you can update these beliefs, and some other move might become the most likely one. But the idea is that you need to have a good initial judgment. If you start with a completely clueless, random choosing, you are not going to be able to converge fast enough. If you want to exactly represent the policy function, you would have to enumerate a lot of this Go tree, just consider all the possible moves and see how good they are in comparison to one another. And clearly this is as difficult as solving Go itself. So we cannot exactly represent this policy function. We need to approximate it somehow. A very popular model for approximating functions, especially in the recent years, are neural networks. in a nutshell, a neural network is a structure of interconnected processing units called neurons that are capable of precisely approximating a function from a sufficiently large number of input-output examples. And each neuron does a very simple thing. It just takes all of its inputs, applies a linear combination of them, and then potentially applies an activation function to the result. A particular neural network that AlphaGo used is called a deep feed-forward convolutional neural network. The architecture I'm going to present now is the most general neural network architecture, and this one is just a very special case of it, where you're going to enforce some of your weights to be the same. So this is what one neuron does. You have some inputs, and the neuron will apply a multiplicative factor to each one of them. So it computes W1 times input 1, W2 times input 2, and so on. You can also have an additive bias to the whole thing. So you have this B factor plus a linear combination of your inputs, the x's. And because this is just a linear model, and usually your problems are nonlinear, you want to be able to express a nonlinearity here. So you will typically apply a function to the output of this, and this function will not be linear. And therefore, it allows you to model far more complex problems than just linear problems. And some popular choices for this function are, well, you can just do nothing. You can use the identity function. A very popular activation function nowadays, and one that has been used in AlphaGo, is the rectified linear unit. And as you can see, it's a very simple nonlinearity function. It's if x is less than 0, set it to 0. That's the engineer's way of injecting nonlinearity into a problem. The function literally looks like that. It turns out it started out as an engineer's way of solving it, and it ended up being something that learns better, performs faster, and is actually more relatable to how actual neurons in the brain work. So yeah, it has been a real success story. But just for reference, in the past, the most popular activation functions were these S-shaped curves called sigmoid functions, where you have this one, the logistic function, 1 over 1 plus e to the minus x, which gives you a value between 0 and 1 in an S shape. And you have a hyperbolic tangent, which gives you a value between minus and plus 1 also in an S shape. Once you're aware of how one neuron works, it's very easy to construct a neural network because it essentially means you have some inputs, and then you have some neurons that are going to consume those inputs, and then you can feed the outputs of the neurons to inputs of other neurons. So that's essentially how a neural network is constructed. And the most general case that you can have is a multi-layer perceptron, where you stack layers of these neurons, and each neuron in every layer will take in every output from the previous layer. So here you have only one hidden layer, and it will receive a copy of all the 3 inputs. Of course, each of these neurons will have their own individual weights. And likewise, the 2 output neurons are all going to have one copy of all the outputs of all the 5 neurons from the previous layer. First of all, training a neural network amounts to figuring out good values for these weights for each neuron. Because once you have the weights and you have a fixed neural network architecture, you can just give it an input and it will produce you some output value that hopefully is the approximation to the function you're after. So you need to figure out what good values for these weights are. And the essential way in which the training algorithm works is you have a bunch of input-output examples, and the algorithm will just do hill climbing, or well, the inverse of that, gradient descent, of a particular loss function to maximize the predictive power on these examples. So you want to design the weights so that it's going to be as good as possible at predicting the output values from the known input values, and hopefully so that it generalizes well to inputs you haven't seen already. And some keywords in this space are the backpropagation and stochastic gradient descent algorithms. So if you're interested in the exact details of how it works, I recommend looking up these terms. The main idea is you have a particular input-output pair. You have your current belief of the weights, so you can feed in the input to the current state of the network. It will give you some output. And then based on the error of your predicted output compared to the actual output, you can compute errors in the output neurons. So you can directly figure out how wrong they are, and based on that, update their weights. And then you can use their error values to, you can propagate them to the neurons in the previous layer and then update their weights and so on. And this is essentially what backpropagation is. It was actually mathematically proven that if your network has only one hidden layer with sufficiently many neurons, and they all have these sigmoid functions, you can arbitrarily precisely approximate any real function. It has that capability, any continuous real function. and this is known as Sebenko's universal approximation theorem. However, unfortunately, the proof of this theorem does not give us a nice training algorithm for figuring out what the weights are and how many neurons we need. And therefore, we cannot really solve problems by just expanding the number of neurons in this one layer. So a response to that was to try to learn complex features of the input by actually going deeper. So rather than having many neurons in one layer, let's have many layers. And this is essentially what deep learning is. A deep neural network is any neural network that has more than one hidden layer. So it can be ridiculously simple. If you have just 2 hidden layers, you have already created a deep neural network. And the whole idea here is that in the past, you would feed in some features that you've computed yourself on the input to the input layer, and then the hidden layer would compute some combinations of these features, and that's great. But when you go deeper, when you have more layers, you can actually feed the raw data into the neural network, and it will give you its own version of feature extraction. So it essentially bypasses the need for handcrafted functions for evaluating the state. And now let's talk about how this applies to the policy network that we talked about before. Initially, the goal of Project AlphaGo was not to create a Go agent. It was to predict what move a human expert would play. DeepMind had this huge database of 30 million position move pairs. So in each position, you know how an expert has played. And based on this, you want to design this policy network, which will tell you for each state how likely it is that an expert would have played a move in a particular position. And after training it for a while, they managed to achieve 67% accuracy on a test set. And this was so much better than the previous best result of 44%. And when they got this result, they thought to themselves, oh, hang on, so this could actually be useful for designing an actual Go player. So this is how it all started. And the ultimate goal was then to be better than a human expert. So you do not want to start by predicting how well a human will play. You want to predict how to play better than a human. So once they got this good initial belief, they trained it further by playing against themselves. So they paired up 2 different versions of AlphaGo with 2 policy networks with different parameters. And based on the outcomes of these games, they would generate further position move pairs for their training, and therefore eventually get even better than a human player is. This is how a policy network can be visualized. So it takes in the initial state of the Go board as the input. It applies some neural network layers. And at the end, the result is this probability distribution. So this is like a bar chart where the taller the bar is, the more likely it is that a human would have played at this position. And this is what we will use as the initial belief for our Monte Carlo tree search. And as you can see, so for a particular Go board, these circles with numbers in them represent the outputs of the policy network. And it's only the outputs of the policy network for which the probability that a human will play there is greater than 0.1%. So as you can see, already training a human expert network significantly prunes the state space, because you could technically play anywhere around here. But in fact, the network tells you that only some of these are potentially useful, and only these 2 are very likely. So this one is 60% and this one is 35%. So 95% probability is contained just within 2 potential moves here. And that's what allows you to be able to use Monte Carlo tree search effectively here, because you have a really nice belief as to which moves are better than others. You can really, really prune the move space significantly here. So there's that component. So it was trained literally just by observing expert moves, and afterwards from self-play with different versions of AlphaGo playing against one another. If these policy values are reasonably accurate, and they are 20% more accurate than the previous best known result was, so that was a really good indicator, we're already very close to achieving a superhuman Go player. But the game of Go can last very long, and we will not usually be able to explore with this full policy network all the way to the end, reliably at least, because we still do discard a lot of moves, and it's just possible that there was a move that we overlooked and that was useful, and just going too deep is not going to work in most cases. So similarly to the alpha-beta pruning algorithm, we're going to stop the search at some point. And once we get to the point where we stop, we want to be able to have an evaluation function to be able to figure out how valuable this state is. This will now also be solved by a neural network rather than a handcrafted evaluation function. So this is one thing that deep learning helps us do. Design custom handcrafted evaluation functions without really understanding what the problem is and what its specifics are. DeepMind also thought that it would be useful to get a very, very rough estimate of how the game would have ended if we were to play it all the way. So they also trained a very shallow policy network, and this one was called a rollout network, and it was trained only on human expert moves. And this essentially is a network that very quickly computes what's the most likely move, and then when you get to this final state after which you're not going to search anymore, you just apply this rollout network for as deep as possible until you reach a terminal state, and then the value of this terminal state, like who won in this terminal state, is something that's also added to the value of the state where you stopped. The value network looks very similar to the policy network. It takes in the state of the board and once again feeds it through a few neural network layers, but the difference is now instead of having a probability distribution at the output, it just gives you one number, how valuable this state of the board is for black. And this replaces the handcrafted evaluation functions that I mentioned for chess and for Arimad. Because it's like a completely standard deep learning approach to the problem, you do not handcraft your evaluation functions, and you can apply a similar approach for many different games. And this one was trained from self-play positions once these were available, because then you could play all the way to the end and just figure out whether this move at this position was, well, contributed to winning for a particular player. And this is how the entire training went. DeepMind had a bunch of human expert positions, and based on that, they trained two variants of the policy network. So this was the one I originally discussed, slightly deeper. It has more than two layers, but this is just for illustrative purposes. So this is a deep network that predicts how likely it is to play a particular move. And this is a shallow one. So it computes it faster, but it's less accurate. This one gives you initial beliefs of how likely a human expert is to play at a particular position. Now, you create many different partially trained copies of this network and have them play against one another. And then you get a lot of self-play position move pairs from which you can train a better policy network. And you can also use these positions to train a value network. So the difference here is you take in the state and you get only one number. And this is how it all integrates with the Monte Carlo tree search. Based on your prior beliefs and the knowledge you've been able to collect so far from searching, you will choose a particular branch to play from a particular position, and then you will do it again and so on, potentially expanding some states, and you will then reach a state where you do not want to explore any further. So you are going to evaluate how good this position is in two ways. So you're going to compute the value of this particular state using the value network. And then based on those values, you can update your beliefs. So you backpropagate these values back to the root of the tree, and then you can update your probability distribution, and you sample again and again. And this is essentially repeated for as long as you have time to play the current move. Also, you're going to use this really shallow network to play out all the way until the end. So this is some terminal state. And based on whether you won or lost, there is a plus or minus one advantage from this very fast policy. And this also gets added up together with the value gained from the value network to obtain the final score for this position. And then you can use this score to update your beliefs in the tree for the next time you want to do this. And essentially, Monte Carlo tree search will just explore a bunch of branches this way as much as it can until its time for the current move runs out. So yeah, once again, you can see Lee Sedol being very nervous. And yeah, this was actually my last slide. Thank you.